welcome back to Fat Mama Physics. In this video, we are going to talk about uncertainty. I'm going to have two videos. The first video, we are going to go over some examples of how you might be able to estimate uncertainty in your measurements when you're doing single one-off measurements. The second video, I'm going to be talking about what happens if you make repeated measurements and how to get your uncertainties from there. Okay, so let's first off with this one. We are going to go over some estimation examples. Before we talk about that, I just want to point out that I do expect you to have a bit of understanding of what accuracy and precision means. At least you've seen some examples. If you've forgotten or you need a quick reminder, accuracy means how close your measured value is equal to the actual true value itself, okay? So for example, if I am actually 165 centimeters and if someone measures 163 centimeters, one person measures 160 centimeters, 163 centimeters is closer to the actual value, which is my height, whatever, okay? The second one is precision. Precision means how consistent you are with your measurements. So let's take height again. So let's say one person measures 160 centimeters. Let's say this person was able to consistently measure 160 centimeters. This person is more precise than the person who, say, measures 163 one time, 165 one time, 170 one time, etc. Okay, so that's precision, making consistent measurements. So now that you have a basic understanding, some understanding of those two words, let's see what that means when we talk about uncertainty. When we talk about uncertainty, most of the time when we do measurements, we don't really know how close we are to the actual value. Sometimes we don't even know what the actual value is, but we try our best and we try to get closer to what we think is the actual value. That's a whole different topic on the how science is a black box. Anyways, we won't go into that one. But most of the time when we do measurements, we can have a really good sense of how consistent our measurements are or how precise they are. So and the way how we convey that precision in our measurements is our use of uncertainties. If our uncertainties are smaller, we have more confidence in our measurement, and therefore we say that our instrument or our measurements are more precise. Okay? So smaller the uncertainty, the more consistent we are with our measurements. So if my measurements span this much range, then I am more precise than if I took a bunch of measurements and they're within this range. Okay, this would have a higher uncertainty, therefore less consistent and less precise. Okay, so that's the idea of uncertainties. Okay, so now we will talk about some examples, how you may make, how can you record uncertainties when you are doing, say, an experiment. Okay, I will here give you some tools. This video, I'm just going to be talking about single readings, okay, single readings. And the most common readings you might use or take are using a timer, a meter stick to measure distance, a mass balance to measure the mass. Let's take a ruler, for example, very common measuring tool, meter stick or whatnot, okay? So here, let's take a look at the first example. I'm going to ignore those blanks for a moment and we talk about this first. So here we have, I snapped a quick picture of a part of the meter stick where this is 40, 41, 42 centimeters, and we're going to measure where this black object, I really don't know what it is. Let's say we're trying to measure this right here, okay? So I'm going to give you, well, of course you would do that to me. So I'm going to give you a quick second to call out your answers, or just to write it down, estimate. What do you think the measurement of this one is going to be? Okay, so then some of you might say, well, this is definitely 41 centimeters, And now we have the little gradients that's going to be measuring in millimeters. So that's 41, 2, 3, 4, 5, 6. And it's somewhere between the 6 and the 7 millimeter mark. And we're not sure what it is. So when you make that judgment call, let me just write here, 41, we know it's 41. We know it's 41.6, but we don't know if it's 40, 61, 2, 3, 4. We have to make a guess. And I'm going to guess 2, okay? You might guess 3, some of you might guess 1, 4, whatever, okay? So this one is an estimate, this last one, okay? And because it still means this number is still significant. Now we can relate this to significant figures. These these digits are all significant, including the 2 is still significant. But since it is an estimate, we need to attach an uncertainty to that estimate. So how to do that? We're going to write a plus minus, and because it's the last digit that we're not sure of, we are going to, and we use this convention in physics, it might be different in your other courses, but in our class, our uncertainty is going to be half of the smallest increment on your measuring device. So on this meter stick, the smallest increment is a millimeter. So our uncertainty here will be half of a millimeter, or 0.05 centimeters. And I'm going to bracket that, and I'm going to put centimeters in the end for our units. Alternatively, you could have done this, centimeters plus minus 0.05, but make sure you have units beside every number, okay? So this is an example how you would make an estimate of your reading and attach an uncertainty to that reading. Okay, so I'm going to write that right there, exactly what I said. Okay, so that is example 1. Here I have a little challenge here, and this is going to happen when you will be doing video analysis this year, when you film a motion of an object and you have to plot it down, which then produces some sort of graph. Okay, what happens when you have, say, pixelated images or videos, or when the motion's too fast in a frame, what do you do? Okay, so that can be applied to that. So here we have a challenge, and this is kind of a one-off challenge. Here I made this picture at the top pixelated, not the ruler. But then what would you do if you have a pixelated image? How would you estimate your reading here? I'm gonna give you a chance to pause the video, think about it, and come up with an answer. Okay, so here are my suggestions. I mean, it's not exhaustive. There's so many things you can do, of course. So now because it's pixelated, well, the first thing you still want to do is you still want to see roughly where that touches the ruler, if I can get this to zoom in properly. So now, I don't know if you can see it, but it's a really fuzzy near the edges. And because of that, I'm just going to put in lines to show where I think the fuzziness stops. You can see that. Okay, and then it starts about there. Okay, so that's kind of the range that I'm looking at right now. Oh, you didn't take it. So right there is where I think the fuzziness stops. That's where I think the fuzziness begins. Okay, hopefully you can see that. And as a result, that looks like my reading is going to be somewhere in between there. I might even have to estimate this as 41.70. Okay, I'm going to do 41.70 centimeters. Okay, so then my reading is going to be where I think where my object cuts off at the ruler. Now, as for my uncertainty, 0.0, or maybe not, that might have to depend where my fuzziness lines are and looking at the range of what that looks like. So it's definitely not going to be 0.05 like in the previous example. And judging from my 2 lines there, it looks like as if it were the length of a millimeter, okay? So that means my uncertainty is going to be 1 millimeter, so that's 0.1 of a centimeter, okay? So whenever you do an experiment and you're not sure, and you look at the uncertainties and you're like, okay, this makes more sense for me to do my uncertainties this way, I highly recommend you go with your instincts, but then when you write your lab out or when you communicate your results, this is when you need to explain the logic behind your choice and your uncertainties, okay? So there's a gray area in which you decide your uncertainties, but then within the range of logic that we can use given what we know, okay? Okay, so here I am actually not done because this is really weird, because you might notice I'm reporting this 0 here in my 100th place as being significant, but then my uncertainties tell me that I am uncertain to the 10th place. I don't even know if I can be certain at all about this 0 here. So here's a rule of thumb whenever you write your uncertainties is wherever your uncertainties end, wherever that place value is, your actual number needs to be rounded up to that same place value. Because I'm already uncertain if I don't even know if my 7 is correct or not, if it's within the range, then how can I even be more sure about the 100th place? It just doesn't make sense. I'm even less sure about that. So I would then take the 0 and do the rounding up to the 10th place so that these 2 place values match up with my uncertainty and with my actual number. So this actually will look like 41.7 centimeters plus minus 0.1 centimeters, okay? So you might have something a little bit different. You might have a slightly different way, but as long as your uncertainties here is larger than what we have here, you are on the right track, okay? So these are just examples of how you can do that. Sometimes, some of you might even know exactly how many pixels we're looking at and might be able to associate how many pixels that you see with the actual measurement itself. And if you can do that, you have your own way of doing it, great, good for you, awesome. But this is just a rough idea of how you would go about that, okay? So, next example here, we have a mass balance. So usually with a mass balance, you would measure your mass, and we use that very often. But as for the uncertainties, we can usually check the brand name and the model number of your mass balance, go online, and you can find the repeatability data that the website has for your particular product, okay? So that's usually what I would do. I don't have the right website for this one, but I have the one for another example. So this is a Fisher brand, and I just picked a random one here, this one that looks like that. Okay, so then if you do a Google search for your model, and you come up with some descriptions, specifications, and so I find this. And there's a lot of numbers, and you might be wondering where to look, okay? Now, 2 numbers hopefully will jump out at you. This one here, linearity and repeatability, okay? So you might think, oh, I'm just going to use this one, plus minus 20 milligrams, because it has a plus minus sign. That's the sign for uncertainty. But we got to be careful when you use these numbers. For linearity, it actually has something to do with the reading sensitivity of the mass balance, depending on how much mass you use. If it's closer to the minimum capacity amount that the scale can take versus the maximum. So what they do with that is they take two equal masses, and they measure one first, they measure the second one by itself next, and they put them together and they measure it again, and they compare the the measurement difference between the two together and then adding the two that were placed on separately, whether or not they're going to give the same reading or not. And that's just to show that depending on how much mass you put on the scale, whether or not it's a linear relationship. Okay, so that does not necessarily tell you about the fluctuations in the reading of your scale. So the number I would actually use for this particular scale would be this repeatability number. So what that means is if I take the same mass and I put it on the scale many times, what's the range of the numbers that I might get? Okay, so that's what you want. It's the uncertainty, the precision in your number that you want. So I would use plus minus 10 milligrams for this scale if you were to use it. Okay, so going back here, yes, we talked about it. Check the company website for their uncertainties. Sometimes it might just be easy. It just gives you a percentage and that's it. So those of you taking chemistry, you have pipettes, you have those micropipetters. No, you don't use it. You might use some volumetric pipettes where you might check the box. They'll have a percentage uncertainty, which then you use that instead. We'll talk more about percentage uncertainties, how to convert back and forth in a later video. Okay, so next one. Example 3. When did the ball fall off the table? Hey, this is exactly what you might do in your Logger Pro or your video tracking software tracking motion. So I'm going to zoom in here. Notice the ball has not left the table at exactly 10 seconds, but has completely left the table at 3 1/3 of a second. So you might be wondering what this 1/30th means. That has to do with how many frames per second your video taking device is able to do. So this particular device is able to take 30 frames per second, meaning that one frame is 1/30th of a second. So this is one frame later, the ball has already left the table. We think that the ball left the table between 10 seconds and 10 1/30th of a second. So how do we talk about uncertainties here? Okay, in terms of when the ball left the table, we know it's somewhere between these two numbers. So then we would say, okay, well, this would be maybe 10 and probably a half of somewhere between here, probably a half of this frame. So what's 1/2 of 30? That's 1/60, okay? So I'm going to say this 1/60 seconds is when the ball left the table, plus minus, and my range of uncertainty is going to be within the last frame and the frame that came afterwards. So that's the plus minus, okay? If I were here, the mid-range where this is 10 1/60th of a second, which is smack in the middle, then my plus minus would range from the middle to here, which is a half of that frame, and here to the previous frame, which is also half of a frame. So that plus minus would be plus 1/60th of a second here, and this would be minus 1/60th of a second here, somewhere between that range. So this is going to be plus minus 1/60th of a second. Okay, now I don't have significant figures here, but that's just the idea of how you would use uncertainties when you're dealing with time and using video tracking software. Okay, so now that's pretty much I have to talk about. So in this video, we just went through a few examples. At the end of the day, every lab, every experiment is going to be different, and you're going to come across new situations, and you have to be adaptable. You have to be critically thinking all the time. And what I'm looking for is I'm not looking for the correct uncertainty, okay? I'm looking for how you're able to think through to get to the uncertainties that you've chosen for your data values, okay? As long as you communicate that, you write it out clearly, explain your logic, we can always work something out, okay? And that's what happens when you eventually have to do a lab or do your internal assessment for IB as well, okay? It's the same idea. Alright, so great job for getting through this video. Hopefully this will be helpful to you. In the next video, we will talk about repeated data and how to deal with uncertainties there. Okay? Thank you for watching this video, and Fat Mama Physics signing out.